In this amazing lecture, we're going to be talking about cymogen matriptase, which is going to be a type of enzyme that you find biologically, right? So to first talk about this, we need to talk about enzymes, right? So an enzyme is going to be a biological catalyst that essentially is going to sequester a substrate, and its goal is going to lower the activation energy of the reaction, right? It essentially does this by being complementary to the transition state of the reaction, right? So how it works is you have an enzyme, then that substrate is going to bind to the active site of the enzyme, right? Once you bind to the active site of the enzyme, usually the activation energy of the reaction is going to be lowered, and then you're going to get a product, right? So once you get a product, you keep the enzyme itself. So that's essentially at its like core what an enzyme does, what an enzyme is, right? So here they start talking about cymogen matriptase, right? So what cymogen is basically the inactive form of an enzyme, right? So basically you can think about it this way. So when you have an inactive form of an enzyme, you can think about like this being the enzyme, and it has a cap on it, right? The active site has a cap on it. So if I like grab this, no air is going in there, right? Because it has a cap on it. And then once it's in its active form, right? The enzyme is in the active form, you can see how air goes in because the cap isn't there anymore, right? So this is essentially the active form of an enzyme. When you put the cap in, you have a cymogen right here because you don't allow the air to go in, you don't essentially allow the product to go in. You can think about it that way. Okay. So now that we know what that cymogen is, whatever, what is matriptase? So what matriptase is? So matriptase is going to be an enzyme that it's going to help in the development of hair follicles. It's going to help in the development of epithelial tissue, right? That's what matriptase is. So yeah, and then what they found out was that the inactive form of matriptase, which is the cymogen, it's actually a little active, right? So you can think about it this way. Back to our example, the water bottle. So a cymogen is supposed to be inactive, right? But if you have the cap like a little bit on, if it's not fully closed, you can see how little air goes in here, right? How little air goes in here. So you can think about it that way. So that's faulty, right? So that's what they found out about cymogen, right? So to fix this, they essentially develop what we call an inhibitor that is going to bind to the active site and it's going to fix that loose cap, right? It's going to fix that loose cap. So what the inhibitor does, it binds to the active site and it fixes that problem, right? And that's what they did in this experiment.
To kind of break down what Jesus talked about, because I know it's very complicated, a quick summary is that matriptase is almost always exclusively seen with epithelial cells, with follicles, with all that jazz, which is a normal part of our body, right? But the thing is, mutant matriptase can also go on to cause skin disease, or more specifically, they've shown in cancer cells when they grab a biopsy and then they test it, and you see a lot of matriptase in those cancer cells, then your prognosis for cancer survival actually goes down. So that's not good, right? So like he said, the matriptase is not only working when it's a protein, but it's also working as its zymogen form. So we have seen not only the matriptase in the cell, but we also see the zymogen matriptase on the plasma membrane. And this zymogen, even though it's supposed to be off for the most part, like most zymogens, this one has enough catalytic activity to control activation of growth factors, signaling the pathways to sustain survival. So the matriptase activity Usually matriptase is regulated by this inhibitor called HAI1 and 2. Our body naturally produces it, and it kind of like keeps it in homeostasis. If you have too much matriptase and too little HAI, then you start going to carcinogenesis, which basically means like increased chances of cancer. So these researchers did something very cool that's not really done in the clinical setting. So they developed an antibody that's not only for the matriptase, but they developed an antibody inhibitor that targets also the cymogen and the matriptase, either glycosylated or non-glycosylated. So this is kind of hard to understand, right? Because it's very complicated. So for those of you that have been paying attention, you might have seen the title, The Jealous Dr. Villa. So I'll give you an example of how we can relate it to real life. So let's say you're Dr. Villa and you're jealous of Professor Donnelly always talking about his NMR machine and how NAU has no NMR machines, AWC has 2 NMR machines, and you're just super jealous, right? So you decide to burn down the AWC building. So you grab a match, you start a fire, and as the fire starts erupting, before it destroys the NMR machine, the fire alarms go off. And it alerts Professor Donnelly, and he goes up to the lab, he grabs both NMR machines and he exits the building. NMRs are safe. He keeps bragging about them, right? So that's how typical inhibitors work. So normally the inhibitors only target the protein once it's actually fully active and fully doing its job. So in this case, the protein would be the fire alarm going off. The cool thing about this is that it will target it before the protein even starts to work. So going back to our example, once again, you're Dr. Villa, very jealous of the NMR. So you decide to, before setting the building on fire, you go into the building and you turn off all the alarms, right? So you turn off all the alarms, you set fire to the building, and both NMR machines are now destroyed. So mission success, you got them destroyed. So that's basically what these inhibitors that the researchers develop do. They'll go in and they'll work on the zymogen before it fully transitions into a protein and starts doing its job fully. So in the clinical setting, it's basically like stopping a crime before it happens. Normally, most inhibitors only target the disease once it's already progressed, once we already caught it, once it's already done its damage. So the cool thing with these inhibitors is that you'll be able to, in theory, slow down tumor growth, signaling by targeting the zymogen before it fully starts going crazy in your cells. You'll prevent activation of downstream cascades. And then it also has very high specificity. So you can directly target the zymogen and not wait until the damage is done, basically. Thank you.
Nothing's like squats. I mean, it's like nothing compares to squats. You can do leg presses, but why? Why do an inferior movement? Why do a movement that looks good, but it produces hardly any results?
Now for the tutorial everyone's been waiting for, we're gonna perform a squat. And we wanted to solidify the understanding in enzymes, right? So when I'm static on the squat, that's when an enzyme is inactive, right? When somebody says go in the background, that's when the enzyme gets active, right? That's when it gets cleaved and it gets active, right? So let's do it.
Go.